Our next speaker is Florian Euchner. He's from the University of Stuttgart, and he'll present to us a really fantastic thing, and it aligns very well with what I've been saying in the past conclusions, which is that we are becoming more and more a quasi-optic discipline, or the focus of the optic properties of radio waves is more and more emerging, and we don't see that we see that more and more. Very recently I was on the airport in Munich, and there was the new scanner of Rode and Schwarz, and it is also able to display shapes of humans and what we're wearing, and possibly weapons or whatever people are wearing under their clothes. And that's an interesting way of detecting those forbidden devices. But this is not just one example, a very expensive example, but you can also do that with Wi-Fi, and that's really cool. And Florian has set up a very interesting project. We're going to listen to his speech now. Welcome, Florian, on the stage.
Yeah, thank you very much for the introduction, and also thank you for giving me the opportunity to present here. So my presentation will be about phase-synchronizing ESP32s. So ESP32s are these ultra-cheap Chinese Wi-Fi chips that most of you are probably familiar with. And what I want to present you is how to build a phased array from them. And one of the applications of this phased array is to build an augmented reality application that, in a sense, makes Wi-Fi visible. The system that I'm presenting is called ESPARGOS, and this slide here shows an overview of the system. So most importantly, it consists of the antenna array, in this case with 8x4 antennas. There is an ESP32 chip behind each antenna, so there are 32 ESP32s in this picture. There's a webcam that sits on top of the antenna array. There is a computer which does some GPU and CPU processing of the data that's collected by the ESP32s, and a screen which then displays a real-time video that's computed on the CPU and GPU. So I will explain lots of the technical details of the system throughout this talk, but I actually want to start with just showing you some video footage that was generated by the system so that you get an idea of what we want to achieve with this, or what this augmented reality application looks like. And this is the first video that I'd like to show you. So here I'm just standing with my phone, and my phone is generating Wi-Fi traffic. And in a second I will turn on the camera overlay from so this is just a visual light camera image, but in a second I will turn on an overlay that's generated by the antenna array, and you will be able to see the Wi-Fi traffic. So this is what my antenna array measures that the Wi-Fi signal looks like. So there's an overlay that makes RF signals, micro F signals visible here. So this is a very simple demo. A more interesting demo is this one here. So here I have a metallic wall standing right next to me. And for visible light, you know that mirrors reflect visible light. For electromagnetic wave, perfect electrical conductors, which are very close to what a metallic wall is, are essentially act like mirrors for RF waves. So depending on where I'm standing, you can either see the reflection or you can't see it. So you saw that when I was in the front, you couldn't see the reflection because angle of incidence equals angle of reflection, so you can only see it when I'm in the right spot. If you do the math, you can figure out that drywall, which is made of gypsum, is more transparent to microwaves than glass, actually. So it's the other way around than when comparing this to visible light. So you can actually see through thin walls with the system. And another funny experiment is to play around with directional antennas, like a Yagi antenna. So obviously, if I'm pointing the Yagi antenna directly at the antenna array, it receives a lot of energy. I mean, kind of what you'd expect. But if I'm pointing it somewhere else, you can hardly see anything because all of the energy is focused in just one direction. Unless, of course, I point the Yagi antenna at the reflector, then you can see the reflection in the mirror, which is the metallic wall here. Yeah. One more fun experiment is to put the transmitter inside a microwave oven. And I expected that the microwave oven would block the signal because it also operates at 2.4 gigahertz, like my Wi-Fi system here, but it doesn't. So I'm still able to track the transmitter while it's in the microwave oven. And the reason for this is that the microwave oven provides around 30 dB of attenuation, which is good enough to not fry you when you're standing in front of the oven. But it's, communication devices are really sensitive to even tiny signal energies. So I'm still able to track the device when it's in this oven. But then I had a different, so here I have a pouch, a bag that was sent to me by a company called Off-Grid. They make these bags for Secret Service, police applications, and so on. And this is what these people can use to hide their devices. So they have some, as far as I know, they probably have some carbon fibers in there that not only reflect the signal, but also attenuate it. So if you want to hide from a tracker, then you will need something more than just a microwave oven, actually. So how does all of this work? So these were some funny videos, but not much of technical content. So to understand how this works, we first need to look at the signals that are sent here. So I mentioned that this is for Wi-Fi, and we're using the ESP32, which is a Wi-Fi chip. So to understand the system, we first need to look at a Wi-Fi packet. So this is what a Wi-Fi packet looks like on the lowest layer. So this is the PPDU structure. PPDU stands for Physical Protocol Data Unit. So this is the lowest layer representation of a Wi-Fi packet. And the one field that we really care about here is the LLTF. So LLTF stands for Legacy Long Training Field. It's called Legacy because it's for the older Wi-Fi standards, 802.11a and G. But newer Wi-Fi standards have similar fields. So there's similar fields for 802.11n, for example, which is then called HTLTF. So this LLTF is a pilot symbol, and a pilot symbol means that the contents of this field are defined in the standard. So both the transmitter and the receiver know what kind of signal is sent during this time. So why would the transmitter send something that the receiver already knows? Well, it's used to estimate the propagation effects. So it's used to estimate the combined effect of time and phase offsets, path loss and attenuation, but most importantly, multipath propagation. So whenever a transmitter sends some Wi-Fi signal, it reflects off walls, it reflects off the ceiling, the floor, and so on. And this causes some distortion in the signal at the receiver, and in order to be able to equalize this distortion, we need to estimate the channel, and this can be achieved with these pilot signals. So let's take a closer look at this LLTF and at the physical signal that's being transmitted during this time frame. And as many of you probably know, Wi-Fi uses a modulation format that is called OFDM. And in a very, very simplified sense, OFDM can be described as we have discrete frequency bins. So here this is the frequency axis, and we have discrete frequencies where we send sine waves at these frequencies, and the information is encoded in the amplitude and in the phase of these sine waves. It's a bit more complicated than that because it has to fulfill some orthogonality constraints. This is the O in OFDM, but this is the basic principle. So we can put a different symbol, a different piece of information on each of these discrete frequencies, and these discrete frequencies are also known as subcarriers when talking about OFDM. So let's say this is the signal that we are transmitting. When we're looking at the signal that we are receiving, it might be a bit different. So for each of these subcarriers, we might observe that the amplitude of the sine wave changes, but also the phase of the sine wave changes. And this is due to the propagation effects that I mentioned. So potential delay over the channel, which will change the phase, or multipath effects, or attenuation and so on, which is going to affect the amplitude. And the nice thing about OFDM is that these subcarriers, these discrete frequencies, are orthogonal in a sense. So there's a very simple mathematical description for this. We can just say that the received signal, which in this case is called YF, so F is the frequency index, it's a discrete index, 1, 2, 3, 4, and so on. YF is equal to H of F times X of F. X of F is the transmitted signal on this subcarrier, and YF is the received signal. Both of them are represented as complex numbers, with the amplitude with the amplitude of the complex number represent the amplitude of sine wave, and the phase of the complex number, the argument of the complex number, representing the phase of the sine wave. So we have YF equals H of F times X of F. And since the LLTF is the pilot symbol, we know that the receiver knows what is being transmitted. So the receiver knows both X of F, because it's in the standard, and it also knows what it received, so it knows Y of F. So from that, it can simply compute H of F. And H of F is known as the channel coefficient, the subcarrier channel coefficient. And the nice thing about using an off-the-shelf chip like the ESP32 is that the ESP32 takes care of computing this H of F for us. So it's not even a software-defined radio, but it's actually a hardware radio. So all of this happens in the silicon of the ESP32. And there's some API that we can use from the source code to get the channel state information from the Wi-Fi radio inside the chip. So how does that help us in creating a camera image? For that, I want to take a look at the scenario we discussed earlier with the metal wall and the point source. So let's say the point source is emitting a Wi-Fi packet. We will then first receive a wavefront from the point source, and then at a later point in time, a reflection from the metal wall. So if we look at what this means for the antennas, for the direct line of sight path, all of the antennas are going to receive this wavefront, but at very slightly different points in time, which will be observable as a phase difference between the antennas. And the reflected path will obviously arrive at a much later point in time. It's all propagating at the speed of light, so really talking about very small time differences here. So the challenge is that we need to synchronize these ESP32s very, very precisely in order to measure these phase differences and these time differences. Yeah, and that brings me to the main challenge, achieving phase coherence in the phased array, or in other words, achieving synchronization. So this brings me to the hardware aspects. Typically, if you wanted to implement a phased array, you would choose one of these two architectures, either an analog array or a fully digital array. The analog array is pretty simple. You just have a phase shifter behind each antenna of the array, and by configuring the delay or the phase shift of each of these analog phase shifters, you can steer the beam of the phased array. So you do all of the beam forming with analog components. The alternative is to have a fully digital array. In a fully digital array, you have an ADC behind each antenna. So you already get the digital samples. You transfer these digital samples to a central processor, which does all of the signal processing, so then you can do the beam forming in software or in an FPGA or something like that, depends on what you have. So these are the two conventional architectures. The architecture that ESPARGOS is using is like a stupid but it works architecture. So if it's stupid and it works, then it's not stupid, I guess. So ESPARGOS is an array of off-the-shelf chips. So it's kind of a mixture between architectures. So with ESPARGOS, we have a complete processing chain behind each antenna, so all the way from the analog signal all the way to the channel state information, but this already includes some digital signal processing. So we are already doing the Wi-Fi OFDM demodulation inside the chip behind each antenna. And then we have like a two-stage digital signal processing, so some parts happen on the chip and some parts happen later on a central computer. So the advantage of that is that it's incredibly cheap because we can use these off-the-shelf chips, these ESP32s. A disadvantage is that we don't get enough array or that much array gain for demodulation. So if you had a fully digital array, you would get a bit more array gain for demodulation. But the challenge remains that we need to do frequency, time, and phase synchronization. So frequency synchronization is the easy part. Usually these ESP32s, they have an input for a crystal oscillator, and instead of attaching a crystal oscillator, we take a 40 megahertz clock and we distribute this 40 megahertz clock to all of the chips on the array. Now the phase and time synchronization is a bit harder, and to understand why, we need to look inside one of these chips, because if you look inside, you will see that there is a component called the PLL, which multiplies the 40 megahertz clock to the 2.4 gigahertz that you need for mixing the antenna signal, the Wi-Fi signal, down to baseband. Now the problem is that the PLL always generates a 2.4 gigahertz signal, but the phase of the generated 2.4 gigahertz signal is unknown. So this is an effect called phase uncertainty. So whenever we turn the input clock off and on again or reset the device, the phase is unknown. And to calibrate for this effect, we need to add another signal generator, another ESP32, which sends a Wi-Fi packet over a well-known channel. So on the back of the PCB, there are microstrip lines, and I know the length and I know the wavelength of the packet on these microstrip lines. And by measuring the phase of the reference packet, I'm able to subtract the phase error and then synchronize all of the ESP32s. So the synchronization then happens in software, and this brings me to the next point, which is the software. How do we go from the raw data from the ESP32s to the camera image? So first I want to show you again the raw data. So these are the subcarrier channel coefficients, the channel state information that I just mentioned. So for every subcarrier, for every discrete frequency in this OFDM symbol, I get a complex number. And so this complex number has an amplitude, which is shown here at the top, and a phase, which is shown at the bottom. And I have multiple discrete subcarriers, so multiple discrete frequencies, and this is the x-axis. And in this case, the Wi-Fi signal was 40 megahertz wide, so I have 117 active subcarriers. So yeah, this is what the channel state information for a single Wi-Fi packet, for a single PPDU looks like. Now, if the transmitter starts moving and continuously broadcasts Wi-Fi packets, then you can see that these curves start to wiggle a bit. So yeah, depending on where the transmitter is, this is this multipath effect that I mentioned earlier, you will see very different transfer functions of the wireless channel. So this was just one antenna, but there are actually more than one antenna. There's actually more than one antenna on the antenna array. So this is what it looks like if we look at 8 antennas. So each color represents one antenna. And every frame of this video is a Wi-Fi packet. So I have lots of Wi-Fi packets here. Now we can collect all of this data in a 3-dimensional array. So just one frame here, one packet, is collected in a 3-dimensional array, which can be represented as a cube. The cube has 3 axes. First of all, the antenna element index in x direction. So we have an 8x4 array. So we have 8 elements along this axis. Then we have 4 elements along the y-axis, so 4 antenna elements there. And then we also have a frequency axis, which, depending on the Wi-Fi channel bandwidth, will have a different number of subcarriers. So yeah, so this is the raw data that we get from the ESP32, and one of these tiny subcubes contains the channel coefficient for one particular ESP32 for one particular discrete frequency. Now, to go from this raw data to the camera image, what we can do is we can take the raw data and then compute a 3-dimensional Fourier transform, so a Fourier transform across all of the axes. That's quite complicated to explain and also quite complicated to visualize. To make it a bit simpler, I want to first focus on a slice of this cube and only compute a 3-dimensional Fourier transform along the slice. So, for example, if we look at just one subcarrier, this is a phase response that we might get from the antenna array. So this might be a measured signal that is the raw data output from the ESP32s. We have the antenna index in x directions, antenna index in y directions, and you can see that the phase increases from left to right over this antenna array. So every square here is one antenna. So for this example, the transmitter might be in front of the antenna array, but a bit to the left and quite far away. you can then compute the Fourier transform over both axes. Then you get to beam space, which looks like this. I will explain this beam space in a second. It's not yet azimuth and elevation. So unfortunately, these are these like very abstract beam space coordinates that we have here. But then we can also zero pad this a bit and oversample the beam space. Then we get an image that looks like this. So now you can really see this yellow circle. This is the beam that we are receiving. And you can also see a couple of side lobes, which always occur when you do this array signal processing. Yeah, so how does this yet relate to the angle of arrival in terms of azimuth and elevation angle? In order to understand that, we need to translate from these beam space coordinates to azimuth and elevation coordinates. And there are formulas for this, which look a bit frightening when shown like this. But there's a simple diagram to interpret this in a much easier sense. So here I overlaid the diagram on top of the beam space image. And now it's quite easy to tell where the signal is coming from. So theta here, that's the elevation angle. And so you can see this here. Theta is the elevation angle, and phi is the azimuth angle. And from this diagram, I can read which beam space coordinates correspond to which azimuth and elevation angles. So here, this yellow circle corresponds to an elevation of around 0 degrees and an azimuth angle of around 15 degrees. Now the final step is to take this information and to overlay it on top of the camera image. To do that, you also need a model for the camera. So you need to either assume a pinhole camera model, or you also need to take into account the lens distortion. But yeah, that really doesn't have much to do with software-defined radio anymore, so I'm skipping over this. And then you get the final result where this RF information is overlaid on top of the camera image. And I just wanted to show you this picture because I thought this was also a pretty interesting result. So here I have the transmitter in this Faraday bag, and then I have a cable inside the bag which is poking out of it, but it's not connected to anything. And somehow the cable now starts conducting the radio wave. So even though the bag is perfectly sealed and closed, a cable now acts as an antenna and like leaks out the RF signal from this Faraday bag. You can also visualize delay. So up until now, we only looked at the slice, but if you also take into account the frequency axis, you can measure the delay of the incoming signal by computing a Fourier transform over frequency axis, so then you get to time domain. Here it's visualized as colors. So you have here outdoors, you have different propagation paths. Some of them are shorter, some of them are longer. I'm holding a transmitter in my hand. And the shorter propagation paths, they are blue, and the longer propagation paths are red. You can even measure relative velocities if you have multiple packets. So this is these are very standard procedures in radar signal processing, but yeah, that's a bit too much for now. But then you'd get a 4-dimensional cube and you can compute the Fourier transform over yet another axis. You can use the system not only for this augmented reality application, but also for localization. Just wanted to briefly show you what it looks like. So here I have 4 antenna arrays. And we are able to track the Wi-Fi transmitter this way. If the antenna arrays are synchronized in time, we can also use time difference of arrival and then multilateration. Or we can just combine angle of arrival and time of arrival information. Yeah, so that already brings me to the end of the presentation. If you're interested in playing with ESPARGOS and you're here on site, then I invite you to stop by at the 50 Ohm booth of the German Amateur Radio Club, where I have a live demo of ESPARGOS. And also just check out the website where I have more information on the project and also channel state information datasets to work with. I'm currently working on trying to get a small-scale manufacturing run of ESPARGOS, but I can't really promise anything there yet and can't really tell when it will be ready because there's also quite a lot of bureaucracy involved there. All right, thank you very much for your attention. I'm happy to answer your questions.
So, thank you very much. Any questions?
yeah, you used a specific device with a specific PDU to track it. Can you also track arbitrary PDUs and actually scan them and actually track multiple devices at the same time?
Yeah, so I will be able to show this at the booth. You can just use your phone, connect to a Wi-Fi network. I need to make sure that your device is on the correct Wi-Fi channel. This is a challenge, and I need to make sure that your Wi-Fi device is generating traffic. But as long as these two conditions are met, then yeah, I can track it.
Is the ESP32 well documented to get these informations, the complex values, or is it difficult to find?
No, it's actually well documented. So getting the CSI is very well documented. I think it's one of the few chips where it actually is well documented. So I talked to manufacturers of other chips, like other Wi-Fi chips like Infineon, and they just told me you're never going to get access to that. But for the ESP32, it's really easy. The thing that's not documented is how to phase synchronize them. So I don't think anyone has tried that before, but getting the CSI is quite easy. Yeah.
Mm-hmm. Okay, thank you.
My question is, it's I guess pretty easy to signal to blend out the reflection and just take the signal who comes first and have so a map from devices where they're exactly to have a map from direct devices, etc. Even if the signal is weaker.
Yeah, so this is basically a very common challenge in indoor localization systems because you never only receive the line of sight path, but you always receive reflections. What helps there is to have a high bandwidth. So indoor localization systems like Bluetooth-based systems, they really struggle with this because they have a small bandwidth. So you're unable to tell which signal comes first and or which is the second. But if you have a very high bandwidth, like 40 megahertz Wi-Fi, then you get a much finer time resolution, and you can, depending on the size of the room, you can tell the signal arrived first and then a reflection came from that other direction. But yeah, of course, the bigger the room, the easier this becomes, and the higher the bandwidth, the easier this becomes.
You used on the ESP32 the C++ or Python library, Python code to program it?
So on the ESP32, there's a firmware written in C. So the firmware is written in C. But then if you actually go to the website, there's an open source Python library that takes care of processing all of the data and generating the image and so on. So that's written in Python, so both.
Okay, one more question.
Yeah, hi. Could you comment on the accuracy, the resolution, and the stability of the channel state information that you get from the chip?
Yeah, so there are some limits to that. The first limit is that for the ESP32, channel state information are signed 8-bit numbers, so I have 8 bits for real and imaginary part. So this already limits the dynamic range to some degree. Then, I mean, the quality of the channel state information depends on the quality of the synchronization, and that in turn depends on things like the amplitude of the reference signal. And so I've done some experiments in that regard, and there are many factors here really, also on the type of modulation that you use for the Wi-Fi packet. Yeah, so I mean, it's not great. It's not great with the ESP32. If you used an expensive software-defined radio, of course you get much higher quality CSI, but you can to some degree compensate for that by just having more antennas. And then regarding the resolution of the camera image, we're quickly getting to the point where we're actually diffraction limited. So we cannot make this image, the resolution of the image, arbitrarily good, because the beam is not arbitrarily small. So these are like physical limits that we're running into.
Okay, so this is a very interesting project. As I said in the beginning, we're going more and more into visualizing visualizing things, visualizing waves live and in real time. And this is really a very, very cool thing. Thank you very much, Florian.